Good day, everyone. My name is Rifan Jawahi bin Jama'in, and this presentation covers my research for assignment 2. So in this presentation, I will discuss the differences between microprocessors and microcontrollers, and also the software translation pipeline, and a comparative analysis between Python and assembly programming. Moving on to the next slide. So this slide outlines the structure of my presentation, and first I will begin by examining microprocessors and microcontrollers and how they differ in architecture and purpose. And next, I will explain how high-level programming languages are translated into machine-readable instructions. And finally, I will compare Python and assembly using a calculator program example. So let's move on to the next slide. So what is an MCU, or a microcontroller unit? So a microcontroller unit, or MCU, is a compact integrated circuit designed for control-based applications. An MCU typically includes a CPU, RAM, ROM, timers, input and output ports, and communication interfaces all within a single chip. It is optimized for low power embedded systems and is commonly based on RISC architecture. So moving on to the real world usage of MCU and the examples. So here are several commonly used MCUs. So the first one will be ATmega 328P, which powers Arduino boards and is popular for beginners and prototyping. And the next one will be the STM32F103, which is widely used in robotics and industrial applications. And the next one will be ESP32, that includes built-in Wi-Fi and Bluetooth, making it suitable for IoT systems. And last but not least, the MSP430, which is well known for its ultra-low power operations. So moving on to the next slide, which is the MPU, or the microprocessor. So what is it? A microprocessor is a central processing unit implemented on a single chip. Unlike an MCU, an MPU requires external RAM, ROM, and also I/O controllers. Microprocessors are designed for high-performance applications and support multitasking and operating systems. So moving on. So this slide highlights several modern MPUs. So for example, the Intel Core i7 processors offer strong single-core and multi-core performance for desktop computing, while AMD Ryzen processors deliver efficient multitasking performance. Last but not least, the Apple's M series, the M1 or the M2, those chips combine CPU, GPU, and neural processing units in a unified architecture. So those are the examples for real-world microprocessors. And moving on to the comparison of the MPU and MCU. So this slide summarizes the differences between MPUs and MCUs. MPUs operate with external components, giving them higher flexibility and processing power, but at the cost of higher energy consumption. And MCUs integrate all components onto a single chip, making them compact, efficient, and suitable for embedded or real-time applications. So moving on to the next slide, which is the compilers, assemblers, and interpreters. So in this section, I will explain how is written in high-level languages, is how it's translated into machine code through compilers, assemblers, and interpreters. So let's start with the compiler. A compiler translates an entire high-level program into machine code before execution. The output is typically an executable file. Compilers perform error checking and apply optimization that improve runtime efficiency. And the next one will be the assembler. An assembler converts assembly language into a machine code, where each assembly instruction corresponds directly to the CPU's instruction set. And assemblers are used for system level programming where hardware control is essential. And last but not least, the interpreter. So, and what does it do? An interpreter executes code line by line. Languages such as Python rely on interpreters. Because no executable file is generated, interpreted programs are easier to test and debug, but generally run slower than compiled programs. Moving on to the next slide, which is the programming language generations. So programming languages have evolved across multiple generations, where each generation increases abstraction, moving from low-level hardware control to high-level human-friendly syntax. So moving on to the first generation language, or we call it 1GL. These are machine code languages consisting of binary digits, and they offer the highest execution speed but are extremely difficult for humans to write and maintain. And the second generation languages, or 2GL. 2GL introduces assembly language where mnemonic codes represent low-level machine instructions, and an assembly requires an assembler for translation and provides detailed hardware control. Moving on to the third generation language, or the 3GL. This language includes widely used languages such as C, Java, and Python. They provide structured syntax, portability, and greater abstraction while still compiling or interpreting efficiently. And moving on to the fourth generation language, or the 4GL. 4GL languages are domain specific and focus on specifying desired outcomes. Examples include SQL for databases and MATLAB for numerical computation. And moving on to the last language, which is the fifth generation language, or we call it 5GL. So 5GL languages are used in AI and logic programming. They work through rule-based systems and constraint solving, enabling the program to infer solutions automatically. So those will be all the generation languages. So now, moving on to the Python versus assembly. So this section compares Python, a high-level language, with assembly, a low-level language, using a calculator program as an example. So moving on to the Python calculator implementation. So this Python calculator shows how simple high-level programming can be. The program asks the user for two numbers, converts them into integers, and performs addition and subtraction, and then display the result. Everything is done using a few straightforward lines like a equals to integer bracket input and sum underscore result equals to a plus b, which makes the code easy to understand even for beginners. This example highlights Python's strength in readability and quick development, where it will let us focus on logic without worrying about low-level hardware details. Now moving on with the assembly code snippet. So this assembly version performs the same addition and subtraction as the Python code, but with much more detailed steps. We need to define memory sections, handle user input manually through CPU registers like EAX and EBX, convert ASCII values to integers, and control system calls line by line. This shows how assembly provides full hardware control but requires more lines of code and deeper understanding of the CPU. It is powerful for low-level tasks but much less convenient compared to Python's simplicity. And moving on to the conclusion. So in conclusion, microprocessors and microcontrollers serve distinct roles based on performance and integration requirements. Compilers, assemblers, and interpreters form the essential translation pipeline between high-level languages and machine code. Finally, the comparison between Python and assembly highlights the balance between ease of development and hardware level control. And that will be all from me. Thank you.